Hi everyone, and thank you for coming. My name is Diana Gergel, and I'm a PhD student at the University of Washington in the Department of Civil and Environmental Engineering. I'm in the computational hydrology group. And today I'm going to be talking about the impacts of climate change on snowpack and soil moisture and tying those changes to fire risk. So there's been a lot of talk this year, and at this conference as well, of low snowpack and forest fires. And someone said yesterday there's sort of an obligatory first photo of low snowpack. I have one of those too. The first photo is of the summit at Snoqualmie Pass earlier this year. And the second photo is of the Okanagan County fire in August this past summer. Basically, this year was a really record low snowpack year and really intense fire year as well. And what this caused, as Undersecretary Robert Bonney said yesterday, was it really refocused and changed the conversation and gave rise to this lively debate over whether or not this year's anomalous conditions are due to climate change or natural variability. I'm not going to answer that question today. However, what I am going to be discussing is the impacts of climate change on snow and fire risk in the western US. And throughout the talk, I'll be using the term SWE. This refers to snow water equivalent, for those of you who aren't familiar with the term. And basically, this can be thought of as the depth of water that would theoretically result if you were to instantaneously melt a snowpack. So our study domain extends over 5 different mountain ranges and 6 lowland regions. So basically, our mountain ranges, this only works for one, obviously, so are the Cascades in red, the Northern Rockies in purple, the Southern Rockies in orange, the Sierra Nevada in blue, and the White Mountains in Arizona. And then the lowland regions are basically the coastal north, the coastal south, the Northwest Interior, the Missouri Basin, the Great Basin, and the lower Colorado. And our study resolution is 1/16th degree, which means about 6 by 6 kilometers. And for our domain, for the mountain ranges, we only include grid cells that have a historical simulated April 1 SWE, mean SWE, greater than 10 millimeters. And for the lowland regions, we only include grid cells that have a historical mean SWE of less than 10 millimeters. So our simulation approach, we use a subset of 10 of the CMIP5 models. These were chosen by comparing precipitation and temperature data from the GCMs to 20th century observations and determining the sort of best performers due to a number of different metrics, which include diurnal variation and amplitude of the seasonal cycle. These were downscaled using the multivariate adaptive constructive analogs method, which I won't say too much about, but it's a statistical downscaling method that utilizes a meteorological training data set to eliminate historical biases and to match spatial patterns in climate model output. So the GCMs were downscaled from their native resolution to a 1/16th degree grid resolution. We used 3 scenarios, historical from 1950 through 2005, and then RCP 4.5 and RCP 8.5. And RCP refers to representative concentration pathways, which are different levels of radiative forcing due to greenhouse gas emissions relative to pre-industrial levels. So then, using max and min temperature, precipitation, and wind speed, we use those downscaled outputs from the GCMs to force the variable infiltration capacity model, hereafter referred to as the VIC model. I won't say much about the VIC model. It's been widely used, but it's a macro-scale, semi-distributed land surface hydrologic model. And we run our VIC simulations at a 1/16th degree resolution, which again means about 6 by 6 kilometer grid cells. So before I get into talking about our results, I want to briefly discuss them in terms, and situate them in terms of climate change projections for the western United States. So first I want to look at winter temperature projections, and winter spanning the months of November through March. And what you see here in the left-hand column is historical 1970 through 1999. winter temperature, and then here the top row is RCP 4.5, the bottom row is RCP 8.5, and the color bar here is change in temperature between the climatological future period and the historical period. And what you really see here is spatially homogeneous increases in temperature. Here it's about 1 to 2 degrees, and then by the end of the 21st century, you're really getting into like 4 to 5 degree increase in temperature. So pretty significant increases in temperature for the winter. When you look at precipitation, however, it's a bit of a different story. And this is because if you sort of look at the differences between mountain ranges, it's not spatially homogeneous. You see differences, and I should say the color bar here is percent change in precipitation. So red areas are decreasing in precipitation, blue is increasing. And this is the ensemble mean, so this doesn't account for differences between GCMs in terms of precipitation projections. And what you see is that in most areas, precipitation is increasing. However, in certain areas, this seems to not be working anymore, so sorry about not being able to point to it. But basically, in the lower parts of the southern Rockies and also in the White Mountains in Arizona, by the end in the bottom right corner for RCP 8.5, you see that there are actually pretty significant decreases in precipitation in those areas, but in the rest of the domain, particularly the Sierra Nevada and the northern Rockies, large increases in precipitation. So now I want to shift to talking about the impacts of warming temperatures and shifting precipitation regimes on snowpack. So here we have time series of historical and future trends in simulated April 1 SWE for all the different 5 mountain ranges. The red line is the ensemble mean, the light gray is the full range projected by the 10 different GCMs we used, and the dark gray is the interquartile range, so 25 to 75% of the GCMs show that. And what you really see is really strong decreases in SWE throughout the 21st century, and particularly between RCP 4.5 and RCP 8.5. And something to note is if you go down to the bottom row and the right corner for the White Mountains, you see that by about 2080, there's pretty much no SWE at all. So the White Mountains are projected to be essentially snow-free by the end of the 21st century. But what does this actually mean in terms of statistical significance? Are these declines, do they look larger than they actually are? Are they statistically significant? So for that, we turn to a heat map, which shows the statistical significance. The boxes that aren't statistically significant are grayed out. The x-axis is the GCMs, and the y-axis is the mountain ranges. And then the color bar is basically the redder a square is, the more the loss of SWE for the future. And then we have 3 different climatological periods, 2020s, 2050s, and 2080s for each of the columns. And you see that the decreases, as in before, are robust across GCMs. Some declines are not statistically significant in the 2020s, but by the 2040s, across all GCMs, all mountain ranges, declines in SWE are statistically significant. So to summarize, there's strong declines in April 1 SWE, robust across GCMs. The largest magnitude of the decline occurs in the Cascades, and the Sierra Nevada and the Northern Rockies are really a close second by the 2080s for RCP 8.5. And then by the 2080s, the White Mountains will be almost entirely snow-free. So another way of understanding these changes is by looking at the effects of warming temperatures in a sort of different manner. Marketa Elsner in 2010, along with others, did some work on characterizing basins as rain-dominant, snow-dominant, or transient based on their average winter temperature. And we adapted this analysis to classify individual grid cells at a 1/16th degree grid resolution to understand how the percent area of each of these classifications would change for the different mountain ranges. We keep the thresholds constant for all the analysis periods. So what this means is that a grid cell, say in the Cascades, which starts off in the historical period with an average winter temperature of, say, -7 degrees Celsius, if in the future period it transitions to, say, -4, it'll become transient. And if it continues to transition between 2020s and 2080s, it might become rain dominant. So what comes out of that, or a way to show that, is this figure. And the first thing that might jump out at you I should say the rain dominant is orange, green is transient, and then purple is snow dominant. And we have historical on the left, and then RCP 4.5 for these three, for the different climatological periods, and then RCP 8.5. And each row is a mountain range. And the y-axis represents fraction of area. So what you notice in the historical period is that there are no rain-dominant grid cells. The reason for that is because by only including grid cells in the mountain ranges that have a historical mean sweep greater than 10 millimeters, we've effectively screened out all the rain-dominant grid cells. But what happens as temperatures warm for RCP 4.5 and RCP 8.5 is that the snow-dominant grid cells gradually shift to being transient. So for example, in the Southern Rockies, you start off with about 50% snow dominant. And then by the end of RCP 4.5 for the 2080s, you have maybe 20%. And then by end of the period, it's like maybe 1 to 3% area is snow dominant. So really significant changes in the classification or the percent area of each of these basin classifications. So now I want to shift to talking about the impacts of climate change on soil moisture. So this figure, there we go, it shows change in mean simulated summer soil moisture in storage between the historical and future periods. As before, the GCMs are on the x-axis, and then mountain ranges are the first 5 rows, and then the second 6 are the lowland regions. And the color bar is the change in mean soil moisture and storage. So it's future minus historical. And what that means is that the red areas are getting drier, so soil moisture is declining. The blue areas are where soil moisture is increasing. So what you notice immediately is that there's a lot of red in the mountain ranges. There's also some gray. The gray squares are declines or increases which are not statistically significant for that particular model and that particular lowland or upland region. But for the mountain ranges, there's a lot of declines in summer soil moisture, and this is particularly strong in the northern Rockies and also in the Cascades. For the lowland regions, there's a less robust signature between GCMs. So for example, if you go down to lower Colorado, you see some blue squares, which are denoting increases in soil moisture, but you also see some red, which are denoting declines in soil moisture. And what this really comes down to is differences in precipitation projections. The GCMs really disagree over whether precipitation is going to increase or whether it's going to decrease. And so the lack of robust agreement between GCMs in terms of soil moisture is coming from this precipitation uncertainty. And the other thing to note is that for the coastal north, you also see a pretty robust decline across GCMs. So to summarize, there's a strong signature of declining summer soil moisture and storage across western US mountain ranges, and that's robust across GCMs. Across the lowland regions, there's really a lack of consistent signature, like I said, except for in the coastal north. And what's really important in terms of thinking about summer soil moisture and storage is that it's very closely linked to fire risk, and this has been well established in the literature. So the projected declines of summer soil moisture that we're seeing we can infer from those declines that fire risk is very likely to increase. And previous studies that have looked at fire risk have really identified the Sierra Nevada and the northern Rockies in the western US as the most at-risk regions for increases in fire frequency in terms of the western US as a whole. And our results support this, but suggest that the Cascades will also be, and already are, at a really high risk for increasing fire frequency. So for our next steps, we really want to sort of bring together vegetation and also climatic impacts on fire risk and sort of bring in the vegetation component in a sense. And so our next step is to model changes in dead fuel moisture to better understand climate impacts on fire risk. That's something we're sort of starting to do now, and we think will bring in another piece of the story. So to conclude, what I have talked about today and shown has been really large statistically significant declines in snowpack and soil moisture, and particularly in RCP 8.5. But the soil moisture story is much more varied in terms of the lowland regions, except for coastal north. And so there's really like a lack of robust agreement between GCMs. And like I said before, this is driven by differences in precipitation projections between GCMs. So to narrow down fire risk projections, we really need a better understanding of how future precipitation is going to occur. And with that, I'll conclude and take questions. I think there's a question right here.
Yeah, we have about 3 or 4 minutes for questions if anybody wants to.
You're basing your prognostication on averages, right?
I'm sorry?
You're basing your prognostication on simulated average temperatures.
Average temperature, yes.
What would happen if you would put some factor showing the extremes? Because it's the extremes to which the systems will be responding.
Well, I guess you mean in terms of the extremes between GCM projections, since some GCMs are projecting larger increases in temperature. Is that what you mean? Or?
Right. Extreme in temperatures, extremes in precipitation, low precipitation, or higher precipitation, whatever. Then you also measuring fuel, dryness of the fuel and fuel loading.
Mm-hmm.
Dry fuel loading should be, bark beetle infestation should be part of it. And again, precipitation levels, moisture stress in trees, lack of moisture in the soil, triggers bark beetle outbreaks.
Mm-hmm.
It's not only the winter temperature or the beetle population in the trees, but it is a tree predisposition which simply calls the bark beetles in and becomes susceptible to the bark beetle because of drought.
Yeah, for sure.
This I would suggest to somehow refine your models in this regard.
Yeah, thank you. Yeah?
Yeah, I was wondering if you could go back to that last slide which you saw showing summer soil moisture.
Sure.
So you were saying that for the lowland areas there wasn't consistent model agreement.
Mm-hmm.
It looks like the northwest interior pretty consistent as always weather.
Yeah, I think there actually is consistent agreement between the models for the Northwest Interior.
Summer soil moisture is getting moisture there. Pretty much every single one of those. That is very hot.
Well, the Northwest Interior is a really large domain the way we've defined it. I can go back to that and show that. It's at the very beginning. So I think really what that comes down to is the way, like the size of the domain, because it's including both higher elevations that don't have a lot of snow and also lower elevation areas. So I think it may be that the higher elevation areas, which might be experiencing more precipitation, are sort of winning out over the lowland areas in terms of, or the lower elevation areas in terms of precipitation projections. That's my guess, although I'm not sure.
So it might be helpful splitting that into smaller, more homogeneous areas.
It could be, yeah.
Just to try to see what the effect is.
Mm-hmm. Yeah.
I think we're about out of time.